For years, the formula for building the world's fastest supercomputer seemed untouchable. Take powerful central processors, add a massive number of specialized GPU accelerators, connect everything with an ultra-fast network, then offload the heavy mathematical lifting onto those GPUs. America's El Capitan follows exactly that playbook. It pairs AMD server processors with AMD Instinct MI300A accelerators and delivers over 1 quintillion calculations per second. Officially, it held the title of the fastest publicly ranked supercomputer on the planet. That era just ended. A previously unlisted Chinese machine named Lineshine has stormed into the official top 500 ranking at number 1. Its verified performance sits at 2.198 exaflops. El Capitan recorded 1.809 exaflops. That places the Chinese system roughly 21.5% ahead on the benchmark that decides the global pecking order. But the real shock is not simply that China grabbed first place, it is how Lineshine pulled it off. This machine pushed past 2 exaflops of sustained double precision computing without dedicated GPU accelerators. No Nvidia GPUs, no AMD Instinct accelerators, no Intel data center GPUs. Instead, Lineshine relies on millions of custom Chinese CPU cores, a proprietary interconnection network, and a domestic software stack. It is the first publicly ranked supercomputer to sustain more than 2 exaflops using CPUs alone. Now, this does not automatically make it the best AI computer in the world. It does not mean GPUs are suddenly obsolete, and one benchmark can never describe every workload a machine may encounter. But the result is official. China has claimed the #1 position on the top 500 for the first time since 2017. And it did so by completely rejecting the architecture used by almost every other leading exascale machine. What does officially #1 actually mean? The top 500 list has ranked the world's most powerful publicly disclosed supercomputers since 1993, updated twice each year. The ranking is decided by a benchmark called High Performance LinPack, or HPL. HPL forces the computer to solve an enormous system of dense linear equations using high-precision, 64-bit floating-point mathematics. The kind of calculation that drives scientific simulation, engineering, and numerical analysis. The benchmark measures how many floating-point operations the machine can sustain each second. A petaflop is 1 quadrillion operations per second. An exaflop is 1 quintillion. Lineshine sustained 2.198 exaflops written out. That is roughly 2.198 quintillion floating-point operations every second during the benchmark. That number is not a theoretical marketing figure. Lineshine's theoretical peak is higher, around 2.736 exaflops. But theoretical peak imagines every component operating perfectly, every cycle fully utilized, zero time lost to communication, memory access, or software overhead. Real machines never sustain theoretical peak continuously. Lineshine converted slightly more than 80% of its theoretical capability into measured HPL performance. That is one of the most important details in this whole story. Building millions of processor cores is difficult. Keeping them busy at the same time is much harder. A supercomputer does not become fast merely because it contains many processors. The processors must communicate, share data, synchronize, and divide a single enormous problem without spending most of their time waiting. Lineshine's 80% efficiency suggests its architecture is not simply large, it is highly coordinated. Inside the CPU-only machine, Lineshine is installed at the National Supercomputing Center in Shenzhen. The machine was built by the Shenzhen Cloud Computing Center and is based on a custom platform called Linekun. At its heart sits a Chinese processor known as the LX2. Each LX2 contains 304 CPU cores running at 155 GHz. The complete system contains 13,789,440 cores. Divide that total by 304, and the architecture uses roughly 45,360 of these processors. That is not 45,000 individual desktop computers. These processors are packed into densely installed computing nodes surrounded by memory, cooling, power distribution, and the network required to connect the whole machine. A modern GPU may contain thousands of smaller parallel computing units. Lineshine instead spreads its work across a vast population of general-purpose CPU cores. The clock frequency of 1.55 GHz may sound modest next to a consumer desktop chip that can exceed 5 GHz, but supercomputers are not built to make one core run as fast as possible. They are designed to make millions of cores work together. Higher clock frequency increases power consumption and heat. At this scale, efficiency, parallelism, and communication matter more than winning a single core benchmark. Imagine trying to move a mountain. One extremely strong worker cannot do it. 45 organized teams might, but only if every team knows exactly which section to move, where to place it, and when to act. Without coordination, adding more workers can make the whole project slower. That is why the processor count is only half the story. The hidden weapon is the network. Every processor inside a supercomputer needs data. A calculation on one node may depend on a result produced somewhere else. If those results move slowly, the processors sit idle at exascale. Even tiny communication delays become enormous when repeated trillions of times. Lineshine connects its processors using a proprietary Chinese interconnect called Linqi. Public technical details remain limited, but the benchmark results reveal this network is doing serious work. HPL involves regular, predictable mathematics, making it easier to divide efficiently than many real scientific applications. However, Lineshine also ranked first on a second benchmark called HPCG. HPCG stands for High Performance Conjugate Gradients. Unlike HPL, it puts heavier pressure on memory access, communication, and irregular data movement. These are the elements of supercomputing that often prevent theoretical performance from becoming useful performance. Lineshine hit roughly 22 petaflops on HPCG. El Capitan achieved around 17.4 petaflops. That places Lineshine about 26% ahead on this second measurement. This result matters because it weakens the simplest criticism. The machine did not merely win one highly optimized matrix calculation while collapsing on a more communication-heavy workload. It also led the benchmark meant to more closely represent patterns found in real scientific applications. HPCG is still only a benchmark. No single test can reproduce climate modeling, fluid dynamics, molecular simulation, seismic analysis, and every other scientific workload. But finishing first on both HPL and HPCG strongly suggests that Lineshine's interconnect and memory system are not afterthoughts. The architecture appears balanced enough to keep millions of CPU cores fed with data. So why build a supercomputer without GPUs? The obvious question is why anyone would avoid accelerators. GPUs became dominant in supercomputing for a good reason. A CPU handles a broad range of instructions. It is flexible, it manages operating systems, complex decision-making, serial code, and workloads with unpredictable branches. A GPU is narrower but massively parallel. It excels when the same mathematical operation must be applied across enormous data arrays. Scientific simulations and neural networks are filled with those operations. That is why America's leading machines all use accelerators. El Capitan combines AMD EPITES processors with MI300A accelerated processing units. Frontier uses AMD MI250X accelerators. Aurora uses Intel GPU Max accelerators. Europe's Jupiter Booster uses Nvidia Grace Hopper superchips. Against that field, Lineshine looks almost deliberately unconventional. One possible advantage is programming simplicity. Accelerated systems split applications between CPUs and GPUs. Developers must decide which code runs where, move data between separate memory spaces, and optimize software for specialized hardware. A CPU-heavy machine can offer a more uniform programming environment. The same processor type handles more of the workload. That does not make programming easy, especially across nearly 14 million cores, but it can reduce the architectural divide between a host processor and an accelerator. CPU-based systems may also perform well on workloads containing complex control logic, irregular memory access, or sections that do not map cleanly onto GPUs. The disadvantage is efficiency. GPUs can perform far more parallel arithmetic per watt on suitable workloads to compete. Without them, Lineshine must deploy an enormous number of CPU cores and keep those cores highly utilized. The machine is not proving accelerators were a mistake. It is proving that accelerator-free exascale computing remains possible when processors, memory, software, and networking are designed as one unified system. This is an entirely custom Chinese computing stack. Lineshine is unusual not only because it avoids GPUs, its major layers are all Chinese developed. The processors are custom LX2 chips. The computing platform is called Lingkun, the interconnect is Linqi, The operating system is K-Lin. The benchmark submission also lists a customized compiler and locally adapted mathematical software. This is critical because supercomputer performance depends on more than silicon. A powerful processor running poorly optimized code can waste most of its theoretical potential. The compiler must translate software into instructions that exploit the processor's architecture. The mathematical libraries must perform common operations efficiently. The operating system must coordinate resources across thousands of nodes. The communication software must move messages across the network without unnecessary delays. When a system achieves 80% of its theoretical peak on HPL, that usually means multiple layers have been optimized together. The hardware team cannot work in isolation. Neither can the software team. The machine behaves less like a collection of separate products and more like one enormous engineered instrument. This full-stack approach may be the real achievement. China did not simply build a processor and insert it into an existing American or European supercomputer design. It submitted a complete domestic platform capable of taking first place on two major rankings. There is, of course, a cost. The power bill behind the performance is substantial. Lineshine draws roughly 42.2 megawatts while delivering its submitted performance. That is industrial-scale power consumption. Running continuously for 24 hours would demand more than 1,000 megawatt-hours of electricity. Cooling the hardware adds. In another massive engineering challenge, every watt entering a processor eventually becomes heat. Thousands of high-density computing nodes must be cooled continuously because overheating can reduce performance or destroy components. Lineshine achieves an energy efficiency of approximately 52.07 gigaflops per watt. El Capitan records around 60.94 gigaflops per watt. That makes the American system about 17% more efficient on the reported metric. This is where the accelerator advantage becomes clearly visible. Lineshine wins the raw HPL ranking. El Capitan produces more computation from each watt. Neither result cancels the other. The Chinese system was designed to maximize sustained high-precision CPU performance. The American system combines CPUs and specialized accelerators to improve performance across traditional simulation and mixed precision workloads. Two different architectural philosophies produce different strengths. In an era when electricity and cooling are becoming hard limits on both supercomputers and AI data centers, energy efficiency cannot be ignored. Winning the performance crown is hugely impressive. Operating the machine economically for years is a separate challenge entirely, and the AI benchmark changes the story completely. This is the most important caveat. Lineshine is officially #1 on HPL. It is also #1 on HPCG. But when the benchmark shifts toward the lower precision mathematics used heavily in artificial intelligence, the ranking flips. The HPL MXP benchmark measures mixed precision performance. Traditional scientific calculations often use 64-bit precision because tiny errors can accumulate and corrupt the final result. Many AI workloads can use 32-bit, 16-bit, 8-bit, or even lower precision numbers. Specialized accelerators are blindingly fast at these operations. On HPL MXP, Lineshine achieved roughly 7.92 exaflops and ranked 4th. El Capitan hit 16.7 exaflops and remained #1. That means El Capitan delivered more than twice Lineshine's mixed precision result. This is why the phrase "world's fastest supercomputer" needs context. Lineshine is the fastest system on the official benchmark used to rank the top 500. That benchmark measures sustained double precision performance. It does not prove Lineshine will train the largest AI model faster than El Capitan. It does not prove it will outperform GPU systems on every application. For AI-style low-precision mathematics, El Capitan's accelerators provide a dominant advantage. Think of the two machines as different vehicles. Lineshine is an enormous high-precision freight engine capable of moving a massive scientific workload. El Capitan is a hybrid machine with specialized engines for different terrain. On the official straight-line test, Lineshine wins. On the mixed precision AI test, El Capitan pulls far ahead. So does no GPU mean the return of the CPU? Not exactly. GPUs are absolutely not disappearing from supercomputing. Accelerator adoption continues to grow across the top 500. AI demand is making specialized low-precision computing more important than ever. Lineshine demonstrates a different point. There is no single correct architecture for every supercomputer. The best design depends entirely on the workload. If a research center prioritizes high-precision scientific simulation, CPU flexibility, and a uniform programming environment, a massive CPU-based design may remain fiercely competitive. If the goal is training neural networks or running mixed precision mathematics, specialized accelerators are very difficult to beat. Future systems will likely become even more heterogeneous, combining CPUs, GPUs, AI accelerators, photonic processors, and custom chips, assigning each task to the hardware that performs it most efficiently. Lineshine stands out precisely because it moves in the opposite direction. Instead of adding more types of processors, it scales one processor architecture to an extraordinary level. That simplicity at the component level creates extreme complexity at the system level. Nearly 14 million cores must operate as one computer. The fact that they do so efficiently enough to reach 2.198 exaflops is the central engineering story. What will China use this monster for? The public Top 500 entry identifies Lineshine as a research system at the National Supercomputing Center in Shenzhen. Supercomputers at this level can support weather forecasting, materials discovery, fluid dynamics, engineering simulation, molecular modeling, and massive numerical research. However, the precise workload mix and access policies for Lineshine have not been fully disclosed publicly. That lack of detail is significant. Benchmark numbers tell us what the machine achieved during controlled tests. They do not tell us how much useful scientific work it completes each week, how easy it is to program, or how reliably it operates under sustained demand. A supercomputer becomes valuable when researchers can use it efficiently. Applications must be rewritten or optimized for the architecture. Scientific teams need access. Storage systems must feed enormous datasets into the machine. The system must remain stable while millions of components operate simultaneously. China has demonstrated the hardware platform decisively. The next evidence will come from published scientific results produced using why this changes the global supercomputing picture completely before Lineshine entered the ranking. The top positions were dominated by American accelerated systems. El Capitan was first, Frontier second, Aurora third. The United States had established a clear lead in publicly ranked exascale computing. Lineshine did not slowly climb from 10th place to 5th and eventually 1st. It appeared directly at the very top. That creates two massive changes. First, the official performance lead has shifted back to China for the first time since 2017. Second, the machine expands the very definition of what an exascale system can look like. The industry had been drifting toward the belief that accelerators were practically mandatory at this scale. Lineshine proves that a CPU-only approach can still win the traditional performance crown. Whether that approach becomes widely copied is another question. The power demand is substantial, its AI performance is weaker than El Capitan's, and the public technical details are not yet deep enough for outside experts to evaluate every design decision. But the result cannot be dismissed. Top 500 accepted the submission. The measured numbers place Lineshine first, and its HPCG result strengthens the claim that this is far more than a narrowly optimized demonstration. Let's be honest about the catch. There are 4 major caveats. First, Lineshine is number 1 on specific benchmarks, not automatically on every real application. Second, its lack of dedicated low-precision accelerators limits its advantage in modern AI computing. Third, it consumes more power per unit of reported performance than El Capitan. Fourth, many architectural details remain proprietary or publicly unexplained. We know the processor core count, clock frequency, system platform, interconnect, operating system, and benchmark results. We know much less about the internal design of the LX2 core, its memory hierarchy, vector capabilities, manufacturing process, packaging, and the exact topology of the Lineshine network. Those details would help explain exactly how China reached this level without GPUs. Until more information or scientific performance results appear, some questions must remain open, but uncertainty around the details does not erase the verified result. Lineshine sustained more than 2 exaflops of high-precision performance and displaced El Capitan from the top of the official list. Here is my take. The number 1 ranking is important, but the architectural divergence is even more important. China did not win by building a slightly larger copy of El Capitan. It chose an entirely different route. America concentrated enormous parallel performance inside advanced accelerators. China distributed the work across nearly 14 million custom CPU cores and built a network powerful enough to keep them synchronized. The American design is more efficient and much stronger on mixed precision AI mathematics. The Chinese design is now faster on the traditional HPL benchmark and also leads HPCG. This is not a simple story of one country possessing better technology in every category. It is a story of two systems optimized around fundamentally different strengths. Lineshine shows what can happen when processor design, networking, software, and system architecture are developed together around one clear objective. It also proves that mature technologies can still produce astonishing, world-leading results. The CPU was supposed to become a supporting actor in the exascale era. Lineshine put millions of CPUs at the absolute center of the machine and reached number one. The question now is whether this is a one-time engineering triumph or the beginning of a broader CPU-first supercomputing strategy. Will China continue scaling the Lincoln platform? Will future LX processors improve energy efficiency and mixed precision performance? Will Lineshine produce scientific results that justify its enormous size and power demand? And will American laboratories respond with even larger accelerated systems? The supercomputer race has not ended. It has become far more interesting because the leading machines are no longer following the same blueprint. So what matters more to you? Should Lineshine be considered the world's most powerful supercomputer because it officially ranks first on HPL and HPCG? Or does El Capitan's stronger efficiency and AI-oriented performance make it the more capable overall machine? Let me know your view in the comments. And subscribe to Empire of Tech for more hard-hitting coverage of the chips, materials, and computing systems reshaping the global technology industry, because China did not take the supercomputer crown by copying the dominant design. It took the crown by proving there was another road to exascale, and that road was paved entirely by Chinese innovation.